So what we're going to be looking at in this video is how we can construct Born-Haber cycles and how we can use them to calculate lattice enthalpies of ionic compounds. And what you need to remember is that these cycles are just applications or extensions of the Hess's cycles that you would have done last year. And remember Hess's law, it's stated here that the enthalpy change for a reaction is independent of the route taken, provided the initial and final conditions are the same. In other words, it doesn't matter which way we go around the cycle, the enthalpy change will be equal as long as we start and end at the same point. So we're going to look at the example of sodium chloride using a Born-Haber cycle to calculate the lattice enthalpy of sodium chloride. So if we look at the information we have been given, it can sometimes be helpful to write equations for these enthalpy changes to ensure that our equations are balanced in line with the definition, and then when we come to do our calculation to see whether we need 2 times the value of the enthalpy of atomization or first ionization energy or so on. So if we just do that off to the side, and we can see the first one we have is standard enthalpy of formation of sodium chloride. If you think about your definition for this enthalpy change, it's the enthalpy change when 1 mole of a product is formed from its elements in their standard states under standard conditions. So sodium chloride, we can see the formula here is NaCl. If that wasn't given to you, you need to make sure that you write the formula correctly using your swap and drop, because that can change all of these equations. So sodium chloride, it's obviously made up of sodium and chlorine. Sodium, in its element form, in its standard state, would be sodium. Chlorine is Cl2. Remember, it's a diatomic gas. And that's going to form NaCl. Now that equation is not balanced. We may be tempted to put a 2 in front of the NaCl and then a 2 in front of the sodium. But that wouldn't be in line with our definition. So what we need to do is put a half in front of the Cl2. Next one is the standard enthalpy of atomization of sodium. And the definition for that is the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. So we're trying to form gaseous atoms of sodium. So we could almost write the right-hand side first of all. Gaseous atoms of sodium. Definition says it's formed from the element in its standard state. The element in its standard state is sodium, Na, and as we said, it's normally a solid. The next enthalpy change is the first ionization energy of sodium, and the definition of that is the energy required to convert 1 mole of gaseous atoms into gaseous ions with a single positive charge. So we're converting 1 mole of gaseous atoms of sodium, so that's just Na. They're gaseous atoms, so we have to have the gas state symbol. It's an atom, so it doesn't have a charge. We're converting it into 1 mole of gaseous ions with a single positive charge, so it's just Na+. Again, it's a gas, so we need to include that state symbol. How we achieved that is that we got rid of 1 electron, so we need to write that on the right-hand side. Next one is standard enthalpy of atomization of chlorine. And remember the definition, this is what you need to be careful with because you can be given bond dissociation energy, which is different. So the enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed. We'll stop there for a second. So 1 mole of gaseous atoms of chlorine is Cl with the gas state symbol. And we're saying that it's formed from the element in its standard state. Well, chlorine in its standard state is a diatomic gas. So it's Cl2. And it has the gas state symbol. But we need to be careful with our balancing. Again, we could be tempted just to put a 2 on the right-hand side. But the definition says it's the enthalpy change when 1 mole of gaseous atoms is formed. So there's just 1 mole of product, so we need to put a half here. Finally, the electron affinity of chlorine. That's the enthalpy change when 1 mole of gaseous atoms is converted into gaseous ions with a single negative charge. It's kind of like first ionization energy, but the opposite way around. So we're going from 1 mole of gaseous atoms and we're converting it to 1 mole of gaseous ions with a single negative charge, and how we do that is we gain an electron. So it's helpful to write those equations. It helps get the definitions in your head, and it means when we construct our Born-Haber cycle we can see whether we need to use 1 times C's value or 2 times C's value, for example. So moving on to the next page, we're now going to construct our Born-Haber cycle. And at the start of any of these calculations, it's helpful to write the equation for the lattice enthalpy of the ionic compound before you even begin. And thinking back to your definition, the lattice enthalpy is the enthalpy change when 1 mole of an ionic compound, so we'll start by writing that, 1 mole of an ionic compound, so that's NaCl, solid, and again make sure you get the formula of your ionic compound correct. It's the enthalpy change when 1 mole of an ionic compound is converted into gaseous ions. So the gaseous ions that make up sodium chloride are Na plus and Cl minus. And they're gaseous ions, so you write the state symbol of a gas. So we're trying to work out the enthalpy change for this reaction, for breaking up the lattice into the gaseous ions. But how we do that is going to be via the smaller steps that we've been given on the previous page, the smaller enthalpy changes. So you can see that we need to break sodium chloride up into sodium and chlorine. Then we need to convert sodium to a gas, we need to convert it to an ion, and the same for chlorine. We need to atomize it and then ionize it. And we'll be able to represent that in our Born-Haber cycle. So we start by constructing a rough outline for our Born-Haber cycle, and then we need to add our equations on the different levels of the Born-Haber cycle. And you should think of Born-Haber cycles as increasing in energy. So I'll just write this briefly and then I'll rub it out to give us room. But as we go up, energy is increasing. So for example, if a reaction is endothermic, an arrow should go up. That's a positive enthalpy change. And if the reaction is exothermic, it'll have a negative enthalpy value and the arrow will go down. Okay, so where we start on the Born-Haber cycle is at the bottom by writing the formula of our ionic lattice. So we can see from our equation above that our formula of our ionic lattice is sodium chloride, NaCl, solid. So that will always be the ionic lattice. Okay. And it's up to you how you do this, but sometimes it's helpful to write the final ions on our last step to remind us of what we're working towards. So where we'll end up is this level here, and what we're ending up with, as we can see from our equation above, is the sodium ion and the chloride ion. Remembering we're trying to work out the lattice enthalpy. And the lattice enthalpy is the enthalpy change when 1 mole of a compound is changed into the gaseous ions. So this is the lattice enthalpy here. And that's what we're trying to work out. But we don't have a value of that, a value for that. So we have to go the other way around the cycle, working step by step. So the first thing we need to do is to split sodium chloride into its elements, and then we work on each of the elements individually. So sodium chloride is obviously made up of sodium, Na, which is a solid in its standard state, and chlorine, which is a diatomic gas, Cl2, and with the gas state symbol. Problem with this is that each of our levels must be balanced in terms of the number of atoms and in terms of the charge. And if you think of our definition of the enthalpy of formation, which is essentially this change here, the enthalpy change when 1 mole of a substance is formed from its elements in their standard states. So we want to form just 1 mole of sodium chloride, therefore I need a half in front of my Cl2. So as we say, this is the enthalpy of formation. And if we look at our values on the previous page, we can see that that enthalpy change is minus 411. And that makes sense with our levels. That's an enthalpy change that's going down, and so it should be a negative energy change. Later on, we'll be taking the reverse of that to get our lattice enthalpy, but we'll come back to that later. So what we're going to do now is we're going to work on our sodium to try and get it from sodium solid to sodium gas with a single positive charge. So what we need to do first of all is change it to a gas, and that's called the enthalpy of atomization. So we're changing it to Na gas plus our half Cl2. We're not doing anything to it right now. So this is called the enthalpy of atomization. And we can see from our values in the previous page that that enthalpy change is plus 107. Again, we're going in the correct direction, increasing in energy. Okay, we're not there yet. We want to convert it to an ion with a single positive charge. That is the first ionization energy. So essentially we're removing an electron from the sodium and it's becoming Na+. We're losing an electron, so we have to write that in. And again, we haven't done anything to the chlorine. That is the first ionization energy of sodium. So we can write that as delta I and then our capital H for enthalpy change. And we are told on the previous page that it is plus 496, the first ionization energy of sodium. Now we can see that the sodium ion is where we want it to be. We've got a sodium positive here in the gas state, and that's the gaseous ion that we have at the end of our lattice enthalpy. So sodium we can leave now, and we finished with it, and now we need to work on chlorine. So we're trying to get it from half Cl2 to Cl minus. What we want to do first is atomize it. So at the minute it's a diatomic molecule, but we want individual atoms. So again, that is called the enthalpy of atomization. We're forming 1 mole of gaseous atoms. So now we will write Na plus and our electron, we haven't changed that. So instead of having half a Cl2, we're just going to have Cl. I'm sorry, I should have my gas state symbol there. So I've just got a chlorine atom instead of a chlorine molecule. And again, here we've got half of 2, which is 1 chlorine, and here we've got 1 chlorine. So we don't need a balancing number in front of it anymore. Okay, that's the enthalpy of atomization of chlorine. And we are told on the previous page that that is plus 121. And finally, we need to ionize our chlorine. So we need to change it from a chlorine atom to a chloride ion with a single negative charge. And what it does that by essentially gaining this electron that sodium lost a couple of steps ago. So it gains that electron and it becomes Cl minus. And what we can see is that we're at our final equation, our final ions. So this is what we call the electron affinity of chlorine. The electron affinity. And that's essentially the opposite of first ionization energy. It's the enthalpy change when 1 mole of gaseous atoms is converted to 1 mole of gaseous ions with a single negative charge. And we are told on the previous page that the value of this is minus 364. And that's why we've gone down again for this cycle, because we can see there's a loss in energy here. So now our cycle is complete. Our equations are written and they are balanced, and we have labelled it with the enthalpy changes, and we have labelled it with the values to make our calculation easier. So as we said earlier, what we're trying to work out is the lattice enthalpy of sodium chloride. We're trying to work out the enthalpy change of this reaction here, the lattice enthalpy. I don't have that enthalpy change, but I have all of the other enthalpy change values. Now what we need to be careful with is with our enthalpy of formation. So remember, I am trying to go from here, sodium chloride, to the gaseous ions. But rather than just going directly, I have to go all the way around. And this is an application of Hess's law, which states that the enthalpy change of a reaction is independent of the route taken, provided your initial and final conditions are the same. So as long as we end up with the gaseous ions, it doesn't matter which way round we go, essentially. So the way round we are going is this way. So what we need to be careful with is that when we do take our first enthalpy change related to the enthalpy change of formation, we're actually taking the reverse of it. We're actually taking the reverse of the enthalpy of formation. So rather than using the value of -411, it will be +411 because we're taking the reverse of it. So now it's time to write out our calculation. And we can see that the lattice enthalpy is equal to the negative of our enthalpy of formation plus the enthalpy of atomization of our sodium plus the first ionization energy of sodium following around our cycle plus the enthalpy of atomization of chlorine plus the electron affinity of chlorine. So if we are going with the arrow, it's adding on that enthalpy change. If we go against the arrow, it's taking away that enthalpy change, as we can see with the enthalpy of formation. So, as we've already said, we need to take the negative of our enthalpy of formation. You can either change that beforehand, as we've done on the cycle, or you can just plug it into your calculation like this. So it's minus the enthalpy of formation of sodium chloride, which has the value of -411, plus the enthalpy of atomization of sodium, which has the value of +107, plus the first ionization energy of sodium, which is +496, plus the enthalpy of atomization of chlorine, which is +121, plus the electron affinity of chlorine, which is -364. If we sort out our signs and open out our brackets, that's going to give us +411 plus 107 plus 496 plus 121 -364. And if you pop that into your calculator, it should give you a final value of +771 kilojoules per mole. You need to include the positive. It'll come out in your calculator just as 771. You need to include the plus sign to show that this is an endothermic change, and lattice enthalpy will always come out as a positive value, and that's because we've got to put energy in to break the lattice into the gaseous ions. So your final answer should always be positive. And that's how you construct a Born-Haber cycle and use it to calculate the lattice enthalpy. So you should get some practice in drawing the Born-Haber cycle and then using it to calculate your value for lattice enthalpy. And it can also be used to calculate any enthalpy change along this way. That could be your first ionization energy or your enthalpy of formation, and that's just a case of rearranging your equation or starting at a slightly different point in your cycle, and we'll do that in a later lesson.